Warm welcome to everyone joining. Thank you for being here. Grab yourself a notebook, a pencil, or a pen. Whichever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. Today we have a problem from the 1996 Calculus BC exam. So this is covering a Calculus BC topic. If you're an AB, steer clear. You probably won't have seen any of this, so don't feel obligated. I guess you technically could still do part A, but I don't think anything else would be practical. So yeah, don't expect to see something like this on the AP exam. For you BC students that is, out there, I just want you guys to know that series and Taylor series are not going to be a major part of the exam. It's occasional that you'll see a series problem on the free response and maybe one or two multiple choice questions. Shouldn't expect that much more than that. That being said, there are some common Taylor series and Maclaurin series that you should be familiar with, which really help you with these questions. That's going to be the Taylor series for e to the x, which we're going to use today. Maybe sine of x, cosine of x. There could be another one or two, but not even the sine or cosine are relevant in this video. Just want to let you know that they do have Taylor series expansions here. The most common one known for e to the x here is basically we just take the powers on x and increase them, and we're just adding all of these terms basically all the way to x to the n over n factorial. Yeah, we will be using that one today. That's why I took the time to write it out. A little crooked, but I think you get the idea. So give yourself like 12 to 15 minutes. Part C and D. Well, part D can be a little bit tricky, but I did just help you with part C and D. And when you're ready, you can join back and see how I approach this problem. Maybe you'll learn something. Maybe you have a better way of doing something. All right, let's get started. So the Maclaurin series for f of x, some function, is given by this 1 plus, and you see the powers going up all the way to n, but the number at the bottom has a factorial that's increasing, and you'll notice that that number is the power on top plus 1. So in other words, if the power is the n, like 2 here, then the number underneath with the factorial, that's n plus 1. So it makes sense that the last term, or the nth term rather, is x to the n over n plus 1 factorial. They want us to find, in part A, f prime. So we have to take a derivative of this thing, kind of. And then we have to do, and plug in 0. And then we have to do the 17th derivative, which we're not going to do one at a time, obviously. And we'll find some pattern. Then we're going to plug in 0. So let's get started with what would happen when we take a derivative. So the first term goes to 0, just to kind of start picking up on the pattern here. F prime, we have 0, and then the first term is going to become 1 on top, because that's the derivative, over. That factorial stays there. It's like a coefficient. 2 factorial happens to be 2, so I'm just leaving it as that. But I suppose I could leave it as, as this. Next term, that's going to be 2x over 3 factorial, right? We're basically just taking the derivative of each term. And so now the terms, not that I have to write all of these out, but now the terms are going to look like this. N, x to the n minus 1, which is basically just like the power rule from how it kind of started out, the derivative of that. It's just the derivative of this term, really, which is just n x to the n minus 1, and then still over n plus 1 factorial. So if I plug in 0, you'll notice that all of these terms that still have an x thing in it, they all go to 0. That first term, however, well, other than the 0, of course, obviously this is 0, but like the first non-zero term here, and only non-zero term is just 1 over 2 factorial, which is 1/2. So that's f prime of 0. Now let's try to pick up on a pattern. If I were to do the 17th derivative, I'm obviously not going to do 17 or 16 more derivatives, right? You're going to have to pick up on a pattern. Well, if I started from the 17th term, that's the only one that's going to sort of survive. All the terms in front of it are going to go to 0. Just like in the first derivative, this term in front of it went to 0, and then it turned into a constant. Everything else still has x's on it, so everything else is going to go to 0 when I plug in a 0. So what I'm saying here is that the 17th derivative would have been the one that survives from taking a derivative 17 times, which the smallest term that does that is x to the 17th. And if each derivative multiplies the power forward, actually, I'm not going to put 17 primes, I'm just going to put 17. This is going to be 17 factorial, still over n plus 1 factorial, so still over 18 factorial. And then, the next term would be like 18 factorial over 19 factorial, x to the 1. And then we'd have 19 factorial, x squared over 20 factorial, and so on and so forth, because this chain is just going to keep on going forever. But the term that became a constant is this right here. So when we plug in 0, we'll just get, 17 factorial over 18 factorial. We have no business trying to calculate what those are, like individually. Well, what kind of 7 is that? It's a weak 7. There we go. This is just going to be 1 over 18. Because everything cancels on top and bottom except for extra factor of 18 on bottom. And then all of these would just go to 0. Every other term would just go to 0. Okay, so that's our two answers. Part B, for what values of x does the series converge? Okay. Well, if you notice, first of all, we should maybe write the series out. Let's say as n goes from 0 to infinity of x to the n over n factorial. If we're adding these terms, if we're basically taking a limit as n goes to infinity, these terms for sure are going to go to 0. So we have reason to believe that it's going to converge. How do I know it's going to 0? Because factorial is bigger than them all. It's bigger than all of them as n goes to infinity. So we know that the terms are going to 0 overall. But to see how it's going to converge exactly, we have to use something called the ratio test, which tells us that the terms are getting so small fast enough. In other words, the ratio of each of the terms, like an plus 1 over an, we want to make sure that this is less than 1. If I'm multiplying with a ratio that's smaller than 1, then every time I'm guaranteeing that my terms are getting smaller. So let's go ahead and write the terms for f of x, which represents like the sum, partial sum of a sequence. We can take the n plus 1 term, which is going to be x to the n plus 1 over n plus 1 plus 1, I guess I can just call that n plus 2 factorial, and then we're going to divide that by the nth term, which is just x to the n over n plus 1 factorial. And if we rewrite this in like a more logical way, as a fraction dividing by a fraction is the same as just multiplying by the reciprocal, then we're going to flip this factorial term. And so much like when we looked at the derivative, the 17th derivative, the n plus 1 factorial on top and the n plus 2 factorial on bottom. That's going to cancel out pretty nicely, and it's just going to leave us with n plus 2. Similarly, these x to the n terms are going to cancel. That's just going to leave us with x to the 1 power. Now what we need to check, sorry, it's not just this ratio that we're looking at. We're looking at the ratio as we go to infinity. So we really should say the limit as n goes to infinity of this. If we just try to, plug in infinity, it goes to 0 over 0 because the terms go to 0. But what we're figuring out here is we're figuring out if the ratio of the terms is small enough that the terms are going to 0 at sort of like a certain speed, sort of like fast enough for us to claim that there's convergence. And so we're basically taking the limit. I guess would be like limit as n goes to infinity. Those things are important to write because they're important. It really represents what we're actually doing here. Looking to see what happens to that ratio some point in the future. And of course, x is just going to be a fixed number. I know we think of x as a variable all the time, but it's just a fixed number because we're using it at some x value, right? And so on the bottom here, we're always going to get that this goes to 0 for sure. The bottom's going to get so large. And so it looks like there's no particular value for x. X can be anything. X is some real number, so we can just say from negative infinity to infinity, or you can also just say all real numbers for all x. Showing the reasoning comes from looking at the ratio and then taking the limit as we go out. That way you kind of keep track of how fast this sequence is going to 0. Because like I said, we know that the factorial is growing quickly. These terms are eventually going to become insignificantly small. But it's about how quickly that happens. Okay, let's go to part C. Now part C says, consider this new function, g of x, which is x times f of x. So it's all of this stuff they gave us up here, just times x to every single term. Write the Maclaurin series for g of x, showing the first 3 non-zero terms and the general term. Cool. Yeah, easy enough. Just multiply x on that bad boy. So 1 times x plus x over, plus x over 2, right? Yeah. X over 2 factorial. So it's going to be x squared over 2 factorial. Then it's going to be x cubed over 3 factorial. That's pretty much all there is to this. Yep. So instead of having the power on top be 1 less, or rather the number on bottom being 1 more than the power on top, we just have them sort of evenly matched. So the nth term is just going to have like an evenly matched power on top and denominator factorial. So that's the Maclaurin series. Really not difficult. But then for part D, we have to use a little bit of like creativity almost. Write g of x in terms of a familiar function. I like the way they wrote that. Familiar. They just have these expectations of you, especially back in, what was this, 96? Jeez, yeah. I don't even know if some of you guys' parents took that exam. Maybe that's how far back it is. Then write f of x in terms of the same familiar function. Okay, that's interesting. What familiar function are we talking about? It's almost like I hinted at it. See this? That's pretty much what we have for our g of x. We don't have the 1. We have this stuff. So what does that mean? Well, that means that if we took g of x, which is the x times f of x, and we add 1 to it, we get 1 plus x squared over 2 factorial, x cubed over 3 factorial. x to the n over n factorial. And this is the e to the x function. So essentially, g to the x just equals e to the x minus 1. That is crazy. So what does that mean about f of x, though? Because g of x is equal to xf of x. So this would be like putting it in terms of a familiar function. But from there, if we want to find f of x, that's going to be g of x over x, obviously. So that's going to be e to the x minus 1 over x. But it needs to converge and work for every single number. So obviously we have to be careful here. Yeah, because this has to be... oh, yeah, that's interesting. Okay, f of x... I'm learning while I'm doing this. F of x needs to be piecewise defined. It needs to be equal to e to the x minus 1. Maybe I shouldn't necessarily just put equals, but I'll put that f of x equals e to the x minus 1 over x, but that's only when x is not equal to 0. So everywhere else it's good. So we need to make sure that it's also good at 0. Let's see. Well, what is... I guess we just have to take a limit. Yeah. We have to figure out what fills the hole. I'm tempted to say 0 or 1, but I want to make sure. So let's take a... This is interesting. Let's take a limit as x goes to 0 of f of x. And that would be equivalent to the limit as x goes to 0 of e to the x minus 1 over x. So of course we're gonna, this goes to 0 over 0. Gonna bust out some L'Hopital's rule. Take a derivative of the top, take a derivative of the bottom, and now we'll be able to send x to 0. And it just is, it's just 1 over 1, so it's 1. Okay, I'm just double checking that. So we need this f of x function to equal 1 when x equals 0, and that is the strict definition for f of x. It will give us the same values as this series, which is why Maclaurin and Taylor series are pretty crazy and very useful. Okay, so A, not bad at all. Just theoretically, take a derivative of these terms. Notice that plugging in 0 sends them all to 0, except for the 1/2 term. And then the 17th derivative, you have to really look into the pattern and make sure that you know what's going to happen by the time you take the 17th derivative. You will have multiplied the powers descending from 17. So that's 17 factorial. Meanwhile, the bottom, which would have been 18 factorial, stayed the same the whole time. Okay, yeah, and then I do want to emphasize that if you're studying and want to answer the series question, and you for sure want to have a confident answer, you'll want to take a look at some of these series. In fact, I'll explain sine of x for a moment. Sine of x, remember that sine is an odd function, right? It's going to be all of the odd terms alternating. So plus x to the 5th over 5 factorial plus ... Cosine, on the other hand, is even. And this is going to be the alternating approximation for cosine. If you use these formulas, however precise you want to do it is up to you. Technically, the next on both of these would be minus. You can find an approximation for sine and cosine. In fact, that's what your calculator does. Believe it or not, your calculator uses a Taylor approximation to get a very good, accurate value for sine and cosine. Yep, just a little extra tidbits of information to bend your ear after maybe a tough problem. So those part D or C even sometimes are going to be approachable if you're familiar with these common Taylor series expansions. There are a couple more. You should look into them. But that is enough blab out of me. I'll catch you guys next time in the void.